Welcome to the derivation of the Slutsky equation, part 2. If you didn't watch part 1 and you're not very familiar with Lagrangians, Kramer's rule, or total differentials, please watch that video first. I'll put a little link to it right here. But if you've already watched that video, let's dive right into this derivation. Now, this is a derivation that a viewer found online. There are a couple of typos or errors in it, but mostly it seems pretty good. And let's just go through where everything comes from. So the first thing, we talked about this in the last video, these are the three first order conditions that you derive by taking the derivative of the Lagrangian with respect to x1, x2, and lambda. Nothing very strange so far. Now what they do is totally differentiate these equations. So they take this first equation here, and they take the first term. This is the derivative of the utility function with two arguments, x1 and x2, with respect to x1. Now, if you totally differentiate this first term, what you're going to do is, this means this is the second derivative, u11 is the second derivative of the utility function with respect to x1. So this is the second derivative of utility with respect to x1, dx1. So just like we did in the total differentials in the last video. But then we also have to take this same term and take the derivative of it with respect to x2. Now this is the first derivative of utility with respect to x1. Now we're going to take the derivative of that with respect to x2, because there's that variable involved in that equation. So that's what this is doing. This is the cross partial, you might call it. This is the derivative of the first derivative with respect to it's the derivative of the first derivative of utility with respect to x1, and then we take the derivative again with respect to x2, and then multiply that times the change in x2, dx2. And then we move on to the next term. Here there are two variables, the lambda and the p1. So first, they take the derivative of lambda p1 minus lambda p1. They take the derivative with respect to lambda. So that's just going to give us minus p1 d lambda. And then they take the derivative of this equation, minus lambda p1, with respect to p1. And that's going to give us minus lambda dp1. Okay? And they take this minus lambda dp1 and they add it over to the other side here. So they add that to both sides of the equation. So instead of having 0 on this side, we have equals lambda dp1. And very similarly for the second equation, we take this derivative of the utility function with respect to x2, and then we take the derivative with respect to with respect to x1. So we get, that's the shorthand here. This is the derivative of utility with respect to x2, and also then you take the derivative of that with respect to x1. Then we take this same term and we take the derivative of the derivative. So this is going to be the second derivative with respect to x2. And that's right here, times dx2. Over here, since we took the derivative with respect to x1, that's times dx1. Minus, same thing here. We have two derivatives. One with respect to lambda, d lambda, and one with respect to p2. And since that's minus lambda dp2, they add that over to the other side. And same thing here. We have the variable m that we have to take care of, and also p1 and x1. And just to make setting Kramer's rule up a little bit easier here, we have, if we were to take the derivative of this equation with respect to lambda, well, there is no lambda. So they put it in here as 0 times d lambda. Why did they do that? Well, because when we set up Cramer's rule, that's what we're getting ready to do in the next part here, we want to be able to have a series of equations with 3 variables. And the 3 variables here are dx1 is represented in each equation, dx2 is represented in each equation, d lambda is represented in each equation, even though in this case it's 0. And then we have the right-hand side. So the right-hand side is over here. So when you set up Cramer's rule, you can solve for the first variable. The first variable here being dx1, we can solve for that first variable dx1, and that's what they're telling us they're attempting to do here, by taking this matrix of coefficients, u11, u21 minus p1, u12, u22 minus p2, minus p1 minus p2, and 0. That would be the matrix of coefficients. However, what we're going to do is replace this first vector of coefficients by the vector of the answers on the equal sign, by these right-hand values here. So that's how we get this matrix right here. So instead of writing it this way, they should write this, instead of these curly parentheses, they should write it with straight up and down lines. So let me try to do that here. That would make things a little more clear here. Straight up and down lines, because this is a determinant, right? And it's going to be divided by this determinant, d. And in this determinant d are these coefficients that I was just talking about. So this d is equal to, let me clean this up so I can tell you that what's going to go in d. I guess we could go ahead and write it down, but it's that. It's these multipliers. Well, they actually tell us, so we don't have to write it down. So they tell us here, look, the determinant of d is, again, they should use these straight up and down bars because that's going to be a determinant, u11, u21 minus p1 right here. u12 from up here, u22 minus p2, right? So they're just pulling those coefficients right out of those 3 equations. So this is just what we did in Cramer's rule in the previous video. Replace the first column with the right-hand side values, but then you're going to divide it by the determinant where you leave all those coefficients just as they are in the 3 equations that you're dealing with here. Okay, so that's the Cramer's rule part. And they tell us, they define their little shorthand here, telling us that uij represents a second derivative. So if it's u11, that means that it's the second derivative. Take the first derivative with respect to x1, second derivative with respect to x1. But if it's u21, it's the first derivative with respect to x2. The second derivative is going to be with respect to x1. Call that the cross partial. Okay, so nothing terribly strange since we reviewed all that in the last video. Now, here's where things start to get a little bit interesting. What they do is they say, look, well, here's what dx1 is. So we're trying to get an equation with dx1 on the left-hand side. We're solving the system of equations for dx1. So what they do is take this determinant. That's really what they're doing, is they're taking this determinant on the top, and they're just leaving this determinant here on the bottom. They're not touching that. So what are we going to do to take this determinant? Well, what we need to do is take the first element, first element, and then multiply it by the cofactor, right? So this is where in this document they tell us what they're doing, but if you're not aware of what a cofactor is, this can be very confusing. So Dij is the cofactor of the ith row in the jth column. Now remember what the cofactor is. The cofactor is a signed minor. Signed minor. So if we're looking at this first element, lambda dp1, then lambda dp1, when we multiply that times its cofactor, it's going to be this minor right here, u22 minus p2 and 0, but signed. So what we're going to have to do is take the lambda dp1 times, remember what we did, we took minus 1 raised to the I plus j, this is just the first row in the first column, so that's going to be squared. So we don't have to worry about that minus 1 because it's going to go away. It's just because minus 1 squared is just 1. And then we're going to multiply that times the determinant of that minor, u22 minus p1 minus p2 and 0. Okay, so that's where they're getting this long term on the top. So let's make sure we understand how they're getting that long term on the top there. So what we've done right here is just the first term in that series, but then we have to add the next term in that series. And the next term in that series is going to involve lambda dp2, right? So we're going to have plus lambda dp2 times minus 1 raised to the I plus j, that's the second row in the first column, so it's going to be to the third power, times the determinant of the minor, which is u22 minus p2 0, right? Now, in the way they're writing it down here, they're simplifying. They're not writing it all out. So I guess we ought not to write it all out, but I'm just trying to show you where they're going with all this. Instead of writing it all out, they're just saying lambda dp1 times the cofactor. So here we have the lambda dp1 times, and all this is the cofactor, and they're just abbreviating this as d11, right? It's good to keep in mind what that d11 is, because we're going to need those a little bit later. Let's go ahead and write the rest of this out. So this is going to be lambda dp2 times, and then here's the cofactor, and that's the cofactor that they're going to be calling d21 in the equation down here. But let's write out what that is, just to get practice, because we're going to be using this knowledge in a few minutes. So that cofactor, that minor, we're going to write, so the cofactor is the sign and the minor. The minor is going to be, we're going to cross out, let's see, we're going to cross out that row and that column. So we're left with u12 minus p1 minus p2 and 0. Okay? So then we have plus, we have another plus here. We've got to take care of the third term down here. So we've got to take that times its cofactor. So we're going to have minus d the budget plus d the price of good 1 plus d price of good 2, and then all that's going to be multiplied times minus 1 to the I plus j, third row, first column, raised to the fourth power, so that's just going to go away. But then we have to multiply that times the minor. And the minor, again, is what we get if we cross out that row and cross out that column. So we get u12 in the first row, u12 minus P1, U22 minus P2 there. Okay? Now, so that takes care of the numerator here. And again, when you're trying to solve, use Kramer's rule to solve for one of these variables, and again the variable here is dx1, we need to divide that by the determinant of the bottom. And that's that. Okay. Let's move on and see what the next part is. So then in the next part they say we want to derive the income effect. So for the income effect, we're going to assume for the income effect we're letting the prices, we're keeping the prices the same, and we're letting the income change. So if we make that assumption, we're setting dp1 equal to 0, dp2 equal to 0. We take equation h, as they tell us, and what are we going to do? Well, anything that has a dp1 or a dp2 in it, we're just going to cross that out and call that 0. So let me get another color here so we can clearly see what we're doing. Let me use orange. So there's a dp1. All right, we're going to cross that out. There's a dp2. We're going to cross that out. All right, then we're left with a dm. We're left with the dp1. We've got to cross that out. And we're left with the dp2. We've got to cross that out. So what are we left after all that simplification? All we're left is a minus dm times d31. And that's exactly what we have right here, minus d31 times dm. Now they changed this to a curly delta m because since we're holding everything else constant, it becomes a partial differential instead of a total differential. That's just a, it is a significant thing, but that explains the notation. Straight D to curly D. A lot of times people aren't very consistent with how they do that. So we're left with just the minus dm times the cofactor d31 and divided by the determinant of the bottom. And then they rewrite that. They rewrite that by going up and saying, well, what is that cofactor there, that d31? Oh yeah, here we go. Here's what that cofactor looks like. The cofactor is going to be, so we have this cofactor, sorry, let me get my orange here. We have this cofactor right here. And they say, okay, well that's just minus 1 to the 4th, so we can kind of ignore that part. And they multiply this out. The determinant here is going to be u12 times minus p2 minus, let me change to yet another color here, minus these diagonal elements multiplied together, u22 times minus p1. So that is what they have written here. They've just rewritten delta m. Well, they've done two things actually. They divided both sides by delta m, so this delta m goes down here, right? So they divided both sides by delta m, so we get delta x1, delta m. Holding prices constant is the little p-bar symbol here. And then they replace the minus the cofactor with minus the determinant right over here. So u21 times minus p2 minus a minus p1 times u22. Because of this minus sign over here, we have to switch the signs up. That's why those switch sides. Okay? Whew. So that is the income effect. So we need to keep in mind, because we're going to use this again. So this is the income effect. Put a purple star there. Now, for the own price effect, next stage here. For the own price effect, we're going to assume that the change in income equals the change in price 2 equals 0. So the only thing we're allowing to change is price 1, the price of good 1. So, again, we're going to take this same equation up here, same equation. I'll highlight it in green this time so it'll stand out. Taking the same equation, and we're going to go through, and everywhere we see a dm or a dp2, we're going to cross that out. And we're going to see what we're left with. Okay, so I see a dp2 here. I see a dp2 here. I see a dm here. And what are we going to be left with? Well, we're going to be left with a lambda dp1 d11 right there. We're going to be left with an x1 d31 delta p1, x1 dp1 d31 right there. And because that dp2 is 0, right, all that goes away, and we're just left with this first term, and we're left with these two terms on the end. And then we rewrite that a little bit. So again, since both of these terms here have a delta p1, we divide both sides by the delta p1. And again, they make that into a little curly d because this is a partial differential now because we're holding constant everything else. So we divide both sides by that, and those two cancel. And then we're left with lambda times this cofactor, x1 times this cofactor. So lambda times cofactor, x1 times cofactor. Here's one of the errors in this handout. They put a lambda here. That lambda does not belong, because when you look at what we have over here, there's no lambda. So this lambda should not be there. So let's cross that out to where we can't see it anymore. It does not belong. So this should be lambda d11 from there. This should be x1 d31 from there. Okay? And then we're still carrying along the fact that we have to divide by that determinant on the bottom. So that's the own price effect. Now, moving right along, lastly, to find the substitution effect, the own substitution effect, we consider that utility is constant in terms of income. So they say we're going to be setting that part equal to 0, and we're going to be setting the change in price 2 equal to 0. So we just do the same kind of thing we've been doing. Let me zoom out a little bit so that we can see that equation up here again. Alright, so let me highlight it in green again, and let's go through. So everywhere we see this we're going to set that equal to 0. Okay, well, we see where that is right here. Well, we're setting that equal to 0, so that part's going to go away. We're going to set dp2 equal to 0, so that makes that part go away. So all we're going to be left with here is lambda dp1 times that cofactor d11. So what do? We divide both sides by the dp1, right? They're moving that down there. You can see it right here. Holding utility constant, holding the price 2 constant, we're left with lambda and then that cofactor d11. Lambda d11. And then the grand finale. They say, therefore, from equation I, j, and k, we get. And so we're just pulling from these three equations. So let me just remind us of a couple of things, and let me get a truly unique color here so that we can see all of this. Let me use brown. Maybe we can see that. So in this first section here, we have, instead of writing this out like this, that's not really helpful. Let's just go back to the way it was written here. So for the income effect, we have delta x1, delta m, holding p constant, p bar, equals minus D31. So minus D31 over that determinant, right? So all we're doing is we're pulling that term and we're bringing it down here. Okay? And we're saying that since we're really plugging into this equation, so since we know that we can write dx1, dp1 holding budget and p2 constant, that's this part of the Slutsky equation right there, equals lambda d11 divided by this determinant. Well, what's lambda d11 divided by that determinant? Well, we saw that down here. Lambda d11 divided by the determinant gives us dx1 dp1 holding utility and the price of good 2 constant. And so they're plugging in that right here. So they're saying this is the substitution effect, the own substitution effect. So this can be broken apart into the first term, which is the own substitution effect from right here. So we're just plugging that in, minus x1 times d31 over d. Well, what's d31 over d? Well, we showed up here that minus d31 over d is the same as the derivative of x1 with respect to the budget holding prices constant. There we go. And so that's where all the pieces of this fall into place. The only one remaining thing, I'm sorry I neglected to mention this, is that there's another typo right here. Again, this is not my handout. This is something that was found by someone else. This should be dp1, right? So dx1 dp1 holding income and the price of good 2 constant is equal to dx1 dp1 holding utility constant and the price of good 2 constant minus x1 times the derivative of x1 with respect to the budget holding the prices constant, which is Slutsky's equation. Now I know I went through that a little quickly, but if you look at the two videos, the one where I set you up for Kramer's rule, total differentiation, and if you follow what we did here, I think you'll be able to follow the steps here and see how we come to this conclusion of Slutsky's equation, which is just the fact that you can take the total effect of a price change and you can break it into the income effect and the own substitution effect. All right? So, I hope I didn't make too many errors there, and I hope I didn't confuse anybody by trying to do this. Please, if there's any suggestions you can make about how I could have done this better. This is the first time I've ever tried to explain this to anyone, and the first time I've looked at this kind of derivation of Slutsky equation in some decades now. If there's anything I could do to answer questions, to clarify anything, please let me know. Otherwise, I'm going to end this extremely long video here, and hopefully this will help you understand how this derivation can be done. I wish you the best of luck in all of your studies.